Hello, my name is Alper Demir, and this is our Eee473 Medical Imaging course project presentation. My group friend's name is Mehmet Batuhan Candar, and the topic of the project is the MRI simulator. Before going further, I want to give a brief information about MRI. Magnetic resonance imaging, MRI, is a type of a scan that uses strong magnetic fields and radio waves to produce detailed images of the inside of the body. So in the scope of the project, MRI simulator was done by using MATLAB. The simulator process can be summarized in three parts: data read and slice selection, case-based data acquisition, and image reconstruction from case-based data. The first thing we have done is to find an appropriate dataset. For this project, brain web dataset is used as it can be seen on the figure. The second procedure is the slice selection. Slice selection in MRI is the selection of the spins in a plane through the object. The principle behind the slice selection is explained by the resonance equation. Uh, Here are the following equations related to slice selection and the flip angle, which are demonstrated as alpha. And the third procedure is the case-based data acquisition. To create a realistic environment, we have included several non-idealities to the signal, and the signal acquired from MRI is denoted as fx of y. And the S of t represents the calculated data from acquired from MRI signal, MRI. These figures shows the sequences of the spin echo and gradient echo pulse sequences. The algorithms were done accordingly. After acquiring the case-based data, 2D inverse Fourier transform is used to get the reconstructed image. To do this, 2D centered inverse Fourier transform algorithm was used. In the scope of the project, the simulator has the following parameters to perform a realistic simulation in a MATLAB environment. There are two pulse sequences, the gradient echo and the spin echo. T1, T2, and the proton density weighted are the contrast models. And for the non-idealities, T2 transverse decaying, chemical shift, and proton density were added. Also, we added a noise factor, and it's an additive Gaussian noise. And we have a selection of slice thicknesses from 1 millimeter to 7 millimeter. For the results part, Batuhan will be present.
As my friend mentioned, we worked on 5 different parameters and present them with different combinations in the following slides as results. For results of non-idealities, we used T1 weighted contrast with gradient echo pulse sequence. We used 1 millimeter slice thickness and noise free in all three of these images. In the first image, we only used T2 decaying and non-ideality, and in the second, we used chemical shift, and in the third, we only used proton density non-ideality. T2 is one of the main contrasting mechanisms for medical imaging and MRI imaging. For proton density, it has a huge impact on the magnetization, and contrast gets better actually. For chemical shifts, as you can see in this one, with the not when there is no with the difference between the non-ideality and only in the chemical shift. In detail, you can see the shift in this figure. Also, these are the used equations for chemical shift. For results of contrasting mechanisms, you can see in the first image, it's T1 weighted contrast, and in the second, it's T2 weighted contrast, and in the third, it's proton density weighted. There are all non-idealities included and 1 millimeter slice thickness used. We used spin echo in these images, but in the proton density weight contrast, there is no T2 decay non-ideality, and the reason will be explained later. The signal of the water is enhanced by T2 weighted contrast, but the signal of the fat is enhanced by T1 weighted contrast. and the difference between the gray shade are explained because of this. And for also when the GX and GY pulses are compared, it can be seen that gradient echo is a bit faster than the spin echo, as you can see from time. And also, this is gradient as echo pulse sequence reconstruction with T1 weighted, T2 weighted, and proton density. You can see with the difference between the white and gray matter shadings, and it's spin echo. Also, you can see that gradient echo pulse sequence and spin echo pulse sequence color codes in these tables. For example, in the T2 weighted and white matter is gray, and T2 weighted and white matter it's dark gray in spin echo. Like you can see this dark gray and this gray. And also for the effect of the noise can be seen especially at the background, especially at the T2 with contrast. Also, when these images are compared to their noise-free versions, images are distorted highly inside the brain. For the effect of slice thickness, we used 1 millimeter cube model brain, and to see the effect of thickness, odd values of 3, 5, and 7 are tried. In 7 millimeter version in the right, and it's the 1 millimeter in the left. In the 7 millimeter version, as you can see, the blur increases highly and edges are become less extensive, as you can see in this comparison. To conclude, we successfully implemented our simulations and had the chance to observe different combinations of different parameters, non-idealities, contrast mechanisms. We also learned that when proton density contrast is used, T2 decay non-ideality causes a problem in reconstruction due to non-values in the increase in contrast. So to show that proton density, we didn't use T2 decay, but we used chemical shift and proton density non-idealities. Next, we will show the implementation of simulation. Thanks for listening. For the simulation, we created a main file to get inputs from the user. If we run this, it asks about the non-ideality. If we enter one for the first one is for the T2 decay, the second is for chemical shift, and the third is for proton density. Let's have all of them. And the contrast will be T2, for example. So let's take it for 1. Use spin pulse and add some noise. You can see the information about the dataset we used, and also to make it more generic, we create different functions combined inside the main function. Actually, it gets the data, then slice selection, then keep space is computed. After that, we reconstruct the image. As a result, we expect to see a figure including created case space, reconstructed image, GX pulse and GY pulse with respect to time, and see a message about simulation completed. All of the codes are written by Alper and Batuhan. We only use the loadming function, which can be found in MATLAB packages, and we only use it for data loading. As you can see, simulation is completed and the image is here. The case space is here. It's the corresponding reconstruct image. GX and GY pulses are there as well. Thanks for listening.